So for this learning module, we'll look at an example problem in the analysis of machines, which will be very important for your final exam. And I'm only going to get the problem set up rather than solve it, and hopefully that tells you something about my plans. So usually the way that these work, so remember that whether it's a frame or a machine, the only thing that matters is that the only thing that would qualify it from our point of view for being that is that if I were to disassemble it into its parts, at least one of the parts would be a multi-force member. This happens to be a machine because it's objective. It has moving parts. If you haven't seen this before, you've lived a blessed life, at least in some respects. I end up using vice grips all the time, oftentimes in order to loosen fasteners that are just incredibly tight. There's nothing comparable to being able to ensure that you keep your grip on, in this case, what they're calling the smooth bolt shank. So you can actually lock the handles of a vice grip versus a plier type assembly. So anyways, it's irrelevant for our point of view. But what usually happens in these types of analysis of machines, and this is a machine because it has moving parts and it's intended to translate the forces that you're applying at the handle to the actual mouth of the vice grips. And we'll notice that the majority of these members, in fact, all of them besides one, are multi-force members. So the way that this analysis usually works is you can actually draw the entire disassembly. Take this and break it at its pins, draw in the equal and opposite reactions on each part. So if you look at this, what it consists of, the upper lip is continuous with the upper handle. So this is one piece, call that one. In addition, you have this kind of adjoining member that adjoins the lower handle and the upper handle. Hopefully everyone sees that since that only has two pin connections and no other forces acting upon it, that is a two-force member. So we know that the reactions at C and D that describe basically the effect that the upper handle and the lower handle have on that member are equal and opposite. So it's either going to be a tension or compression. You could probably guess which way it actually works in a vice grip when you squeeze. You have this lower handle of the assembly here. So that's 3. You have the lower jaw, 4, and you have the actual bolt that you're applying the force to. So there's actually 5, and this isn't even considering the pins themselves. There are 5 FBDs of parts you could draw, and you can draw them all. However, you need to realize that ultimately what you're interested in is the magnitude of the compressive force that's actually being applied to the bolt. So the 2 of these assemblies that we talked about, the 3 things that you might be interested in that you'll have to draw a free body diagram on, at least one of them, is 1, 4, or 5, because those are the only bodies that actually involve the force of interest. Now, the other thing that we have to do usually, because you think about it, if you tried to solve, let me show you like what would happen if you drew the free body diagram of 1 and tried to solve it directly. So I am not an artist, so apologies in advance. My general rule of thumb when I'm drawing ugly is I just make the lines thicker and hope no one notices. So call this the upper handle, call this 1. So you have the applied force at D. You have the reaction at D that this 2-force member exerts on the upper handle. So we know that it's going to be directed along the line of action of that member CD. So I'll just call it FCD. Okay. I have at point B here, that is not a 2-force member, so its reaction, generally speaking, will have an unknown Y component and an unknown X component. In addition, I have the force that the actual bolt exerts on the upper lip, which is going like this. That's actually the quantity that I want to solve. So I put a little star by it to say that, hey, that's what I want to solve for. But if you look at this, right, we know the applied force is 5 pounds. However, we know the direction of this reaction associated with the 2-force member, but we have one unknown there. We have 2 unknowns here, and we also have the unknown that we're trying to solve for. So as this free body diagram is drawn, it has 4 unknowns, which is going to mean that it's statically indeterminate. So even if it is stable, we can't use our equilibrium indeterminate. We can't use our equilibrium analysis of rigid bodies because we can only write 3 equations. So it must be naturally that the kind of component of this assembly that's going to allow us to solve for what we need is this lower jaw. So if you notice, right, the bolt would exert a downward force upon it, right? We would have equal and opposite reactions at B. In addition, we would have these reactions at E. And since we haven't committed to describing them anyway, I'll just draw them up and to the right. Usually like the technique I use, not like I have the best technique at doing it, but if I haven't committed to drawing something yet, I draw them in the positive direction. And then when I draw the reaction pair, I draw them back in the negative direction. So you might say, okay, this one, you did an even worse job, Henry, because this has 5 unknowns. And that is true. However, look at what happens if I take the lower handle and I know that I have the applied force F. I know that I have the equal and opposite reaction of the two-force member. So this would be FCD. And I can describe its geometry from the information that I'm given. And in addition, I have this, the reaction pairs of E. So if you notice, this lower handle is statically determinate because there are only 3 unknowns. So the best way to go about doing this problem would be to enforce equilibrium here. Now you think about it. It's tempting to say, I don't need any of these reactions. I wasn't asked to find EY, EX, or FCD. However, you were asked to find N. And if you can borrow the information for EY and EX from the analysis of this lower handle, right, then all of a sudden this becomes statically determinate. So this is the thing I want you to see, that this would be statically determinate. If you knew EX and EY. So that's the way that this analysis is going to go. You're going to analyze the lower handle and then analyze this handle. In terms of enforcing equilibrium here, I think the easiest way to do it is to first enforce rotational equilibrium about point E. And what that's going to allow you to do is solve for FCD. So what you're going to want to do is from the geometrical information that you're given, you can actually decompose FCD. So if you notice FCD is going to be directed along the axis of member CD. And if you notice, it follows a triangle. And I want to make sure I draw in the information for you correctly. That is, let me actually extend it a little bit, similar to a 1 inch high, right? There's 1 inch separation between B and E. We're talking about between C and D. If you notice, this is a 1 inch vertical displacement, so it's 1 inch. And horizontally, that's a 3 inch displacement. So what that means is you can write FCD as, what would that be? So this hypotenuse would be square root of 10. So FCD would be minus 1 over root 10, whatever that magnitude is, minus 3. Sorry. That's always be careful, right? This is why you have to, even though you've done this problem all semester the last few weeks, look that in this case, the sine, the x component, I should say, is opposite of that angle. So it would be 3, and this would be 1. Always check yourself on these things because you don't want to do, it's so much work. And imagine if you end up losing points just because you make one small mistake like that. So that's your decomposition. And if you notice, when you decompose this into x and y components, the only dimensions you need to compute the moment about C for the, remember that, sorry, I'm stumbling over my words here. For the vertical component, you'll need this separation, basically the distance between E and C, and you have that 1 inch. And for the horizontal component, Do you even need that? Well, if you look, right, we're kind of given the indication that C and E lie at a kind of constant point in the xy plane. So you won't even need any physical, what word am I looking for? Sorry, it's been a long day. I know I always use that excuse. Perpendicular distance for the x component, because the x component, the line of action, will go right through E. So you're going to be able to write an equation for the moment about E that only involves the y component of FCD and F1. So once you've enforced rotational equilibrium about point E, then you can do sum of all forces in the x equals 0 and sum of all forces in the y equals 0. And that will give you EX and EY. And then once you have that, go back and enforce equilibrium here. And remember, the quantity that you're ultimately interested in is this this normal force that the bolt exerts on the mouth of the pliers, which is equal and opposite to the force that the mouth of the pliers exerts on the bolt. So if you enforce equilibrium of this, if you know EY and EX, all you need to do is write one equilibrium equation here, that the moment about B has to be 0. Because if you notice, even the y component of E is going to pass directly through B, so it won't contribute. Clearly, none of the forces that are associated with the reaction of B will contribute. So fundamentally, all that this involves is it's a function of EX and the quantity that you want, N. And do be careful that in the geometry that you're given, that N is actually shifted from the vertical by 20 degrees. So you'll need to decompose N as well. So hopefully that is helpful for helping you get started. Again, if you're like, man, I wish you would have just solved the problem, there's a reason that I didn't solve the problem directly. So make sure you know how to do this. And if you have any questions about how to do this particular problem, just shoot me an email. I'm also happy if you want to, like, hey, I got this answer. Is that correct? I can check it for you as well. So I will see you all. Actually, we're done with chapter 6. So we'll be moving on to chapter 7, which is internal forces. We're going to kind of go over the idea of a normal force and a shearing force and a bending moment. And then we will draw the big problem I want you to do for that, because when people think about taking a statics class, the big pain is drawing these bending moment diagrams and the shearing force diagrams. So we will be doing a lot of that, but it's basically just all we're going to do is apply the method of sections, assume something about the internal forces, and compute how they change as we move in distance along the span of the beam.